I'm at Klaus Blaum Group at the MPIK in Heidelberg, and there we recently constructed an experiment with the purpose of measuring the G factor of the 3 helium nucleus. And we have already completed one such measurement where we actually measured the 3 helium plus hyperfine structure, from which we can also get the nucleus G factor. So as a first slide, I have give a slight motivation for this. So measuring the hyperfine structure gives access to basically 3 constants, one of which is the bound state electron G factor. And that you can use to compare it to state-of-the-art theory values. Then there is the shielded nucleus G factor. So as compared to doing the experiment with the 3 helium 2 plus, you have still a shielding of the electron. So the value you extract from the experiment is a shielded value. But still, because the theory is so good, we can use this value, subtract the shielding basically from theory, and then we can use this to establish 3 helium as accurate NMR probes, as also Mariusz Puchalski explained on Wednesday. And because currently there are only indirect measurements of the 3 helium G factor as, where they compare it to H2O samples, for example. And those are very much limited by the accuracy with which the H2O shielding is known. Okay, so here you can also see a small table which highlights the advantages of using 3 helium as compared to water. I mean, 3 helium is a very easy system. It's an atomic system, and that decreases systematics and also makes the theoretic calculations of the shielding much easier. Okay, so here you can see past measurements, past indirect measurements of this value. There's also some small discrepancy. And then the last value we can extract is the zero field hyperfine splitting constant, which is composed of the Fermi term and then some corrections and also some nuclear corrections. And those are limiting in the theory, and then we can invert this to extract some nuclear structure of the 3 helium nucleus, namely the CMAC radius. Okay, so hyperfine structure of 3 helium plus, it's a very simple system. There's a single electron interacting with the nucleus, and then we do this in a magnetic field. So this is basically the Hamiltonian of the system. You have the interacting spins here. This is this set zero field hyperfine structure splitting. Here you have the electron and nucleus magnetic moments, which are connected to the G factors. And you can already see this is what makes this difficult. It's the same as in the proton experiment. The nucleus magnetic moment is very small, and this is what makes the more direct determination with the nucleus only much more difficult than doing this hyperfine structure measurement. So we did this first. Okay, and here you can see the Breit-Rabi diagram of the 3 helium plus. And essentially, you have these 4 states. In the high field limit, they go over to just spin states of the nucleus and the electron. And essentially, by flipping the electron spin, you get transitions in the 150 gigahertz regime, which are very close to the transitions you get just for a bound electron. And then you have these smaller transitions here in the range of 4.6 gigahertz, which are mainly flipping the nucleus spin. Okay. So how do we do G factor measurements? Or here now the hyperfine structure measurement. So you have here a level diagram again. These transition frequencies are functions of the 3 parameters and the magnetic field. So in order to extract these parameters from the measurements, you need to know also your magnetic field to a high accuracy. And you do that by simultaneously measuring a cyclotron frequency. So the cyclotron frequency is just the precession frequency of a charged particle inside a magnetic field that is directly proportional to the B field. So by using this, we can invert this and extract the G factors and the hyperfine splitting. And you can already see this hyperfine splitting constant is just the sum of the two frequencies here. And it's essentially magnetic field independent, which makes it a bit more accurate to determine in our experiment. Okay. So I will now briefly talk again about how we do these single ion measurements in a panning trap. You've heard this before, so we'll be quick, hopefully. So we have a static magnetic field, which gives the radial confinement. To give an axial confinement, you use an electrostatic quadrupolar field. And by applying this, and we do this by applying essentially 3 voltages, we actually split the radial motion as well. So we get 2 radial motions, a fast cyclotron motion, a magnetron motion, the sum of which is the cyclotron motion. And here the axial motion, you tune via this voltage here essentially, and you can get a very accurate and robust measurement of the free cyclotron frequency by square adding those frequencies like that to get the magnetic field. And typical values for our experiment, this reduced cyclotron frequency is at 30 megahertz, the magnetron frequency at about 5 kilohertz, and the axial frequency at about 500 kilohertz. So you can already see this is the most important value to measure. The other ones have some decreased impact on your accuracy. Okay, so how do we do a frequency detection? So we connect to one of the electrodes a coil, a superconducting coil, which gives us a high Q resonator. And then over this resonator, the image currents the ion induces while it oscillates here get amplified essentially to a somewhat measurable voltage. The other benefit of this is that this resonator thermalizes your ion to its own temperature. And our experiment is at 4 Kelvin. That's how we get our ion essentially to 4 Kelvin. Okay, so this is at a fixed frequency. And what you essentially do is you adjust your ion's frequency to sit on top of this resonator. Okay, and when it sits on top of the resonator and then it fully thermalizes, so it only has amplitude corresponding to the 4 Kelvin of your resonator, you get this dip spectrum here, which is the spectrum of a thermalized ion. And then, now I'll be very quick, you also can apply RF excitations on your electrodes here. And this we use to do manipulations of the ion, and we can also couple the radial motions to the axial motion, which is the only one we can directly detect. Or if you have a cyclotron resonator, you can also detect this directly. But if you couple those, you can essentially extract the cyclotron frequency via measuring these 2 split axial frequencies. Okay. So now we know how to measure the cyclotron frequency, and from that determine the B field. And now we need to also measure the spin state of our ion. So for us, it's not only 2 states, but we have 4 states in the magnetic field in the hyperfine structure. So I'll write it like that. So you take this additional B2 term, as you saw before. We do that by using a nickel ring electrode in a different trap. And that essentially couples your spin state to the axial frequency. And then you can, by changing the spin state, you can resolve that. But for our case, we can only resolve the changes of the spin state if we change the electron spin. And the spin state change of a nucleus, we cannot directly observe. That is, or at least it is much harder to observe that. That's why we can use a trick. I will show that in the next slide. So this is how it looks like when you change the spin state in this trap. You can clearly see that you can resolve that. That is the electron spin. Okay. So what we do now, I mean, we want to also detect the changes of the nucleus spin state. And we do that via a double resonance technique, essentially. So if we, for example, want to know in which nucleus state we are. So we are now really in this state. So we drive this transition and this transition alternatingly. And then, depending on which transition actually produces a measurable electron spin flip, you know in which nucleus spin state you are. So that is how we measure then the nucleus spin state, by mapping it to the readout of the electron spin. Okay. So now I will I will explain the measurement scheme. So because of this B2 term, you get a broadened resonance, and that is why you use 2 traps to do the full measurement. You can see here, this is how a measurement would look like if you would do it completely in the analysis trap. So you use 2 traps and transport between the traps. So you have one trap where the B2 term is essentially very small, and then the other one where it's very high, where you can detect the spin state. So you do a spin state determination first in the analysis trap, transport it to the precision trap, do a simultaneous measurement of your cyclotron frequency while irradiating the Larmor frequency, or the spin flip drive in this case. Then you transport back to the analysis trap and check whether you changed your spin state. So it's essentially a counting experiment. Okay, here you can see our setup on the right. You can see some messy cabling and how it's inserted into our cold bore magnet. So this is a 5.7 Tesla magnet, which has a cold bore. So you directly insert the experiment into the liquid helium of the magnet reservoir. You can see that it's about 2 meters in absolute height, and we have to induce microwaves at 150 gigahertz into the setup, and we do that via some oversized waveguides. So we have a horn antenna on top here, and they shine in the microwaves all the way down here to the traps. You can see here a little bit closer view of the trap chamber. And in our case, as opposed to, for example, alpha trap, we don't have external access to this trap chamber for ions. So we produce our ions inside the trap chamber. The trap chamber here is closed off as to ensure a very good vacuum. And right at the bottom, we have the detection coils. So they thermalize to 4 Kelvin in the best way possible. Okay. Now a close up to our penning trap setup. As I showed you before, we have this precision trap here, an analysis trap. This is separated. But now let's go through how we produce our ions. For producing the 3 helium inside this trap, we use a 3 helium filled glass sphere. So helium, as it is the smallest atom, diffuses basically through anything. And you can use that. We do that by having a sphere here, which we can heat via just a resistor. So at 4 Kelvin, essentially no helium diffuses into the trap. And then we actually only have to heat it to about 100 kelvins. So it's actually diffusing less out while we do the experiment than when the experiment is warm. But that's still sufficient to then use a field emission point to shoot electrons through the trap stack to ionize those few helium atoms and produce a single 3 helium plus ion. Okay. And then, as I said before, the microwaves shoot through from the top. And we also have some coils here to introduce the 4 gigahertz excitation we need for the nuclear spin flips into the trap center. Okay. So now I will actually go directly to the results. That's basically the specialities of our experiment, which I just showed. So with this, we could measure 4 transitions, 2 at this 4 gigahertz and 2 at the 150 gigahertz. And you can see here that the 4 gigahertz transitions have a width of about 1 hertz, while this is at about 150 hertz. So actually the relative width here is a bit better, which is due to those transitions being a bit less dependent on the magnetic field. So this width is essentially limited by our magnetic field determination of the cyclotron frequency. Yeah, this has been completed now. And the group of Zoltan Hamann contributed also from the MPIK, contributed some theory calculations for the electron G factor. And this is our final result. So first, the electron G factor determined experimentally is in agreement with the theoretical value. Theoretical value is quite a bit better in precision. And then the nucleus G factor. So I give the value here for the shielded one. You can see here, and this is about a factor of 20 better than the old indirect measurements, and it's a direct measurement. And for the hyperfine splitting, we reach quite a bit better relative uncertainty. And our theory colleagues use that to extract the Semach radius to a few percent, to this accuracy here. Yeah, and essentially we're statistics limited, but it was pretty close with the systematics, and that is some error which we could actually solve pretty easily. It was a residual magnetic inhomogeneity in our precision trap, which essentially limited us. Okay, to summarize, the motivation essentially was to measure the nucleus G factor to calibrate NMR probes. And the test of the shielding parameters will be possible if we measure 3 helium-2+, which is still on our agenda. We can determine some nuclear structure from our result. We avoided the direct nuclear detection by mapping it to the electron spin state. We measured these four transitions to extract the G factors. And now quickly, the next steps. I mean, we still want to do this direct measurement. For this, we have to improve our setup quite significantly. Namely, we need to increase our frequency stability in the analysis trap. This is essentially what Barbara was talking about. So you need a low temperature. So we are also working on this sympathetic laser cooling. And then we are currently, because we're waiting on some new stuff for our experiment, we're currently also looking into measuring the beryllium 3+ hyperfine structure, and possibly also for lithium 6 and 7. And there we're also would also help if some theoreticians told us if this is actually interesting. Okay, thank you for your attention.
Thanks for the nice talk, Stefan. Any comments or questions, Christoph?
So what is your value for the G factor of 3 helium?
You mean the unshielded one?
The G factor of 3 helium nucleus.
I don't have it here, but I can tell you that it's the 3 helium plus shielding is in agreement with the value Marius Puchalski has calculated.
This I do not understand. What is an agreement? Means you use this G factor to determine 3 helium magnetic moment, and then you compare with other measurements. Okay. So you mean that your bar G factor, the magnetic moment of 3 helium nucleus is in agreement with other determinations?
No, I mean, okay, here is the shielded value.
Yes.
This is the one we extract directly from our experiment. And then in order to compare it, we have to calculate it to the nucleus G factor, and then possibly to compare it to the atomic
Maybe you
value.
Don't need to calculate, you just can look on the paper, someone other has calculated.
Yes, yes.
And then you just perform subtraction of 1 and divide, and then you get the G factor. Is it a complicated calculation?
I mean, we have to, this is done in the paper, but I can tell you there's no significant deviation.
Well, that was my point. There's no significant deviation from the other determinations.
There is some discrepancy which we can attribute to the water shielding, essentially. We can calculate a water shielding from this, and this is in a slight discrepancy to all the measured values. Because all the indirect measurements are limited by the water shielding.
I know. This is So this is very important because this would mean that you improve the magnetic moment through helium. It's not only it's more accurate, but also it's different. It's important. Regarding the hyperfine splitting of this of the other elements, I forgot it was lithium-6, lithium-7, what?
Beryllium.
Beryllium. I would say it is very interesting because we know from the helium-like and lithium-like, lithium-like lithium, of the hyperfine splitting in atomic lithium and helium-like lithium, that there is a significant anomaly in 6 lithium. I mean, the Zemack radius is very much different from between the lithium-6 and lithium-7. We don't understand why.
Mm-hmm.
Maybe it's a mistake in the calculation, but if you can measure and confirm this, because hydrogen theory is much simpler, I mean, hydrogenic-like theory is much simpler, this would be proof that this magnetic amount, that something is going on with the 6 lithium, that it has a very anomalously large Zemack moment. I mean, by Zemack moment, I also mean the nuclear parasitic correction, just everything what is just this hadronic contribution. So I would say this would be very interesting to confirm, because so far there is a recent Chinese measurement, which from the lithium plus, which confirms the anomaly, but you can measure it, I personally, much more accurate because the theory is infinitely accurate. For this is, I mean, for point nucleus. And for 9 beryllium also will be very important, because then I will explain you why. Because if you do that for 9 beryllium, then Terka predictions for atomic hyperfine splitting will be much more accurate, because we are limited by the Zemack radius in 9 beryllium.
No.
So all the atomic, then we can give a very accurate predictions for the atomic hyperfine splitting. So this is, I would say, it will be pretty interesting to get this. So
yeah, I think also one difficulty will be finding those transitions in the first place, maybe. So
yeah, but it's on the, I'm talking about the hyperfine splitting, not magnetic moment determination.
Yeah,
so,
I know, but if we do this measurement, we have to find these hyperfine transitions first, and this could prove a bit difficult if it's not previously
fine transition because you don't know where it is placed. Or?
Yeah. But I have not quite looked it up if it's
anyway
how accurate it should be possible.
Yes, it's very difficult, but anyway, I would say it's an interesting project. So, and coming back with in your paper, which we soon published, I believe, you present the result for the bar nucleus G factor.
We present the result for the bar nucleus G factor. Yes.
Thank you very much.
I was just wondering on slide 11, what is going on with the chi-square?
This is not a curve. This is no fit, as in we fit this to int values. We do this actually via a maximum likelihood estimation. And we also estimated some how probable this is in comparison to a flat background and like 4 sigma significance. But we have some more resonance curves at different powers. So this is like, taking out 2 of those.
Just looks like the error bars are too big.
These here?
Well, these, yeah, it's a question. What do they mean when you have a background at 0? But even at the peak, you have all the error bars. You know, the spread is much less than the error bar.
I mean, okay, there's like 2 values nearly off the curve from 10 values. I think that's okay.